Hi everyone, my name is Nkangala. I'm an electrical engineering lecturer at Nkangala TVET College Witbank campus. Today I'll be assisting you with Engineering Science N3. This is the book that we'll be using, or that I'm using, by G. Oliver. So the topic that we'll be talking about today is friction. What is friction? So we're going to deal with horizontal movement, horizontal motion, and the movement on an incline. Okay, now what is friction? We know that friction opposes the motion, right? So now we have what we call the static friction, and the kinetic friction, right? And the static friction, it opposes the initial movement. So it means it's just the force that is required to move a body. And then we have a kinetic friction. Kinetic friction. This one, it opposes the force, that causes movement after a body is in motion. So it's important to differentiate between the two, the static and the kinetic. The static and the kinetic. And then we have what we call the coefficient of friction. Coefficient of friction, this is the formula. For a static friction, we're going to have US equals to the frictional force divided by the normal force, right? And then for the UK, for the kinetic, it will be the frictional force also divided by what? The normal force. Remember now that the normal force is equal to the weight. For example, let's say we have a box on a plane like this. There's a force applied in that direction. Obviously, we're going to have the frictional force in the opposite direction. Then this is the weight of the object due to mass and gravity. We're going to get the weight there. And there's a normal force. This is our normal force. Now, if you can look at the diagram, the normal force is going up, the weight is going down. Meaning now our normal force is equals to the weight. And also our frictional force, it will be equals to the force applied. This will be equals to that one. Or you can simply say this plus that, it will give you 0, right? Now, we have what we call now, since now we know these are the formulas that we can use to calculate the coefficient of friction, we have what we call the angle of friction. The angle of friction now, it is the angle, for example, here. It will be the angle here. That is the angle of friction there. Now, how do you then calculate the angle of friction? How do you then calculate the angle of friction? If we look at our diagram, this is the resultant. As you can see now, if we close there, we have a triangle. This is the 90 degrees. We have a triangle there. Now we can rename this, for example, to say A, B, C, D. Right? A, B, C, D. And then now, as we can see, the distance from AD is the same as BC, which is our frictional force, right? So AD is equals to BC, which is our frictional force. And then AB is the same as our our DC, which is our normal force. AB is the same as DC, which is our normal force. Now, we want to calculate this angle. We want to calculate this angle. What do we have? In this case, we can see that this side AD is opposite to the angle, and this is adjacent to the angle. So we're going to use tan theta, meaning now tan theta is equals to AD there. AD divided by the adjacent, which is our adjacent DC. And then this is the same as AD is equals to the frictional force, and then DC is equals to the normal force there. Is equals to a normal force. So as you can see now, we have tan theta, the frictional force, and the normal force. And this, if you can check this, it gives us our coefficient of friction. Meaning now this is the same as saying this is the coefficient of friction. So calculating the angle now, calculating that angle, you're going to say theta is equals to arctan mu, which is the same as saying arctan, the frictional force, and the normal force there, right? So that is the angle of friction. That's the question that they can ask you on this one. That is the angle of friction. Now, let's check the angle of repose. What is the angle of repose on the inclines? The angle of repose on the inclines. Let's say that we have an incline like this. This is the incline, and then this is the angle theta. And then we have an object or a box that is placed here. In this case, we know that there will be weight, mg, right? There will be weight, mg. By the look of things, we're going to break this force, this weight, into two components. The perpendicular component, which is that component. Why are we saying it's perpendicular? Because it's a perpendicular to the incline. The perpendicular component, this is our weight, perpendicular, and the horizontal component in that direction, the weight parallel, right? Now, we're looking for this angle, of which now this angle is the same as this angle. That is our angle of repose. By the look of things now, if you look at this object here, obvious the direction it will move, if you just leave it like that there, it will slide down, move down the incline. Why? Due to the gravity component, which is this one. Now, a more simplified diagram, it will be drawing something like this. We have a box, and then if it's going to move in that direction, look at the weight parallel. It's in that direction. This is the weight parallel of the box. Obviously, we're going to have our frictional force in the opposite direction. And then this is our weight perpendicular. Then we have our normal force. Now, from this diagram or from this statement, we can simply see that the normal force is also equals to the weight perpendicular there. And then the weight parallel is equals to the frictional force. Meaning now, this angle, if we want to calculate this angle, remember you're going to say opposite over what? Adjacent. So tan theta, it will be the opposite. Opposite here too, it's our W parallel over the adjacent, which is this one, because this is adjacent to the angle, this side is opposite to the angle there. Now, tan theta, remember now we said W parallel is the same as the frictional force. So we have our W parallel there, and then our W perpendicular is the normal force, right? So what you've noticed is that on the inclines, it's not like this one on the horizontal, where now we say the tan theta is the frictional force over the normal force, or it will be the frictional force over the weight. Now, on the inclines, it will be the weight perpendicular, not just the weight perpendicular, right? Okay. Now, let's do an exercise. Let's do an exercise first. I'll take an exercise from the book, exercise 4.1, number 10. The exercise reads as follows. A block with a mass of 80 kgs is pulled across a horizontal plane with a force of 300 newtons. This force is sufficient to overcome friction. Calculate the coefficient of friction between the block and the plane. Now let's analyze our diagram. We know if it's moving in that direction, we're going to have frictional force in this direction. We have the weight of the object. This is the weight due to mass and gravity. We have the normal force there, right? Now, what else do we know? We know that the coefficient of friction, or the formula to calculate the coefficient of friction, it will be frictional force divided by the normal force, or the weight. Now, we need to calculate now the weight. The weight, it will be the mass of the object, which is 80 kgs multiplied by 9.8. 80 times 9.8, we're going to get something like 784 newtons. Now, this weight is equals to the normal force, which is that normal force. And also now, our frictional force is also equals to the applied force. F applied, which is 300 newtons. Meaning now we can substitute to our equation saying now our frictional force is 300 divided by 784, and then we're going to get the coefficient of friction. 300 divided by the answer there. We're going to get 0.383. The coefficient of friction doesn't have units because the newtons are going to cancel the newtons, and then this is our coefficient of friction. Now, I'm going to do the second problem, whereby now we have this very same scenario, or something more like in this fashion, but now on an inclined motion. I will also take an exercise from this book, exercise 4.1, number 17 in this case. Number 17, we are told that a block with a mass of 32 kgs is placed on an incline. So we have an incline. The angle is 14 degrees. We have a box. The mass of the box is 32 kgs. The mass is 32 kilograms. And they say the frictional force is 11.5. The frictional force, 11.5 newtons. Now, they say, A, you calculate the parallel weight component, the perpendicular weight component, the smallest force required to pull the block up the incline, and then the last question, it will be the smallest force required to pull the block down the incline. Now, let's analyze that. We know that we're going to have our weight due to mass and gravity, 32 times 9.8. We're going to get the answer there, 313.6 newtons. So this is our weight. Now we're going to break this into two components. We have that component which is going down there, the weight perpendicular because it's perpendicular to the incline, and this component, the weight parallel, which is parallel to our incline. We have the normal force. The normal force. For now, I'm not going to put the direction of whether we're pulling the block up or down because we still have to calculate for A and B. A, we are asked to calculate the parallel weight of the component. The parallel weight of the component. This is the weight. This is the component that is parallel to the incline. So A, we're looking for this component. If you can check now, it's more like we have a triangle like this, a right angle triangle like this, where our hypotenuse is the weight, our opposite is the parallel, and then our adjacent is the weight perpendicular. So if we look here, this angle, remember, is the angle of repose, the one that we calculated earlier, which is the same as this angle of the incline, 14 degrees. Now, we're going to say opposite over adjacent. If you can still remember, we have this thing that says soccer tall, which helps us to know the size. Now this is opposite. We're looking for this side. This side. What do we have? We have the hypotenuse. We have the angle. So we're going to say opposite and hypotenuse. What is that? It's sine. So sine theta. It will be our opposite. What is opposite? This one parallel divided by the weight, because the weight is our hypotenuse. But now we're looking for this one. Meaning now we're going to make that one substitute to the formula. W parallel, it will be equals to W. W is 313.6 sine, this times this, we just cross multiply, sine 14. And then we're going to get the answer there. Sine 14. We got 75.867 newtons. We rounded off to 3 decimal places after the comma. This is A. And then B, they were looking for the perpendicular weight. The perpendicular weight of the component. B, if we're looking for the perpendicular weight of the component, we're looking for the perpendicular weight of the component. This is what we're going to do. Meaning now we're looking for this component. This is B. This component, what do we have? We have the hypotenuse and the opposite that we just calculated, which I don't encourage students to use the answer that you've just calculated if you have an option to use the one that was given to you, because this one might be wrong. So I prefer to use that one. So I'm going to say, I'm looking for this. I have this one. The adjacent, the hypotenuse, that is cos. Meaning now cos theta is equals to my adjacent, which is the weight perpendicular divided by the weight, which is our hypotenuse. Meaning now the weight perpendicular is weight cos theta. And then the weight, we calculated the weight is 313.6 cos 14. Cos 14. And then when we punch that in a calculator, we get 304.285 newtons. Now, this is our weight perpendicular. This is our weight parallel. Now, C, they were looking for the smallest force required to pull the block up the incline. Now, the smallest force required to pull the block up the incline. If we're going to be pulling the block up the incline like this, this is our F up. It means now we're going to have our frictional force in that direction. This will be our frictional force. Now, what I do now, I simplify the diagram, or I draw something that I can see. If I draw the same incline with the box there, I have my F up here, the frictional force in the opposite direction. Now, what do I have here? The weight perpendicular, which is that one. I have the normal force there. And then look at this component. This component, it's facing in that direction. So it will be proper or better to put it here, the weight parallel. Then this is our incline. Remember now, I'm looking for F up. If I'm looking for F up now, this is C. If you look at this, these equations, this plus this, it will be equals to that one. Or the sum of all the forces that are parallel to the incline, it will be 0, right? So now we have this one, which is this one, the frictional force, the F up. Now we're going to say F frictional plus the weight parallel is equals to the force up, right? Is equals to the force up. Meaning now our force up, it will be equals to the frictional force. The frictional force was given as 11.5. 11.5 plus the weight parallel, which we just calculated, which is this one, 5.867. And then the answer that we get when we punch on the calculator, we get 87.367 newtons, right? This is our F up. Now, the last equation, the last statement or the last question now, it was to calculate, D was to calculate if we're pulling down the incline. If we're pulling down the incline now, it means we're pulling down the incline, this will be the F down, and then now that side will be our what? Our frictional force. That will be our frictional force. Then now, if you want the equation for that, you have F down here, the force down, the weight parallel is still in this direction, and then this will be the frictional force in the opposite direction. Meaning now, if you say force down plus the weight parallel is equals to the frictional force. The frictional force. The question was to calculate for the force down, and then we can make this one the substituted formula. F down is equals to the frictional force minus the weight parallel. Now, the frictional force was given to us as 11.5 minus the weight parallel, 75.867. And then the answer that we're going to get here, as you can see, we're going to get a negative answer. It's negative 64.367 Newton. What does this mean? It means now the block there, even if it didn't apply a force, it's sliding on itself. That's what it means. It's sliding on itself there. Slide by itself. That's what it means. Slide by itself there. And also what you've noticed is that now that we're going up, the only thing that we're checking is the direction. It's either we're moving up or we're moving down, right? Now, I would like us to solve one of the questions from a previous question paper. This is 26 July 2018, question 4. Now, on the question, they say a casting with a mass of 500 kgs rests on a surface slope. So, we have that. And then what do we know? We know that the mass is 500 kg. They say the slope is 20 degrees. The slope is 20 degrees. Now we are given the coefficient of friction, which is 0.25. Which is 0.25. This question is out of 12 marks. And then now we were asked to calculate the component of the weight that is perpendicular. That is number 1 for 2 marks. The component of the weight that is parallel, and then the friction between that one. Okay, let's analyze our diagram. We know that we're going to have weight. This is weight, mg. We're going to break this into 2 components. That component, which is the weight perpendicular to the incline, and this component, which is the weight parallel. Then this is the angle, which is 20 degrees there. Now, they say a casting with a mass of 500 rests on a surface with a slope of 20 degrees to the horizontal. The coefficient of friction is that. A, we are asked to calculate the component of the weight perpendicular to the incline. Now, the one that is perpendicular to the incline is this one. Now, we're going to do the same thing, which is adjacent hypotenuse. Meaning now, we can calculate the mass here, 500 times 9.8. The 500 times 9.8, the 500 times 9.8, we're going to get 4,900 newtons. And then now, what are we looking for? What are we looking for? We're looking for this component. Now, calculating this component, what we're going to do now, we're going to say adjacent hypotenuse, that is what? Cos 20 is equals to the weight perpendicular divided by the hypotenuse, which is this one, 4,900. Then we cross multiply. Therefore, our perpendicular, it will be 4,900 times cos 20. And then the answer that we're going to get there is 4604,494 newtons. And then B, we are to calculate for this component. We are to calculate for that component. This component now, we see that is opposite hypotenuse, meaning now sine 20, it will be equals to the weight parallel divided by our hypotenuse. Meaning the weight parallel, it will be equals to this, which is this one, 4,900 sine 20. 4,900 sine 20. So 4,900 sine 20, we're going to get 1675.899 Newton. This is the parallel weight. And then now, question number 3, we were to calculate the friction between the casting and the incline. We were to calculate now the friction between the casting and the incline. If we're looking for friction now, remember, looking for friction, if we analyze this, if this block is just placed on an incline like that, it will freely flow, or this will be the direction, it will go down due to the component or the weight component, this component, meaning we're going to have our frictional force in this direction, and then there will be a force in that direction, right? Now, we want to calculate our frictional force. We are also given the coefficient of friction. We know that coefficient of friction is the frictional force divided by the normal force. But now, on the inclines, we say the normal force is equal to the perpendicular weight, which is the same as saying frictional force divided by the perpendicular weight. Now, we can substitute. We have a 0.25 equals to the frictional force, which is unknown, divided by the perpendicular force, which is this one that we calculated, 4604.494. Then we can make F substitute to the formula, meaning now this multiplied by that, it should give us the answer, 0.25 times 4604.494. We're going to get 1151.124 newtons. This is the frictional force. And then now the last question was to calculate the smallest force required to move the casting down the incline. Now, to move that down the incline, meaning now the force, they're looking for the F down. The F down. If you're looking for the F down now, what do we have? What do we have? This is what we have. Now that we've analyzed our incline, we have an incline, a box there, the frictional force in that direction. Now we want to calculate our F down. Our F down, we're going to say F down plus the weight parallel, these two, they're in the same direction, equals to the frictional force there, right? And then now, we're going to make this one substitute the formula. Making this one the substitute the formula, the F down, it will be the frictional force minus the weight parallel, right? And then now, our frictional force, we've calculated our frictional force previously. This is the answer for our frictional force. And we also solve for the weight perpendicular. The weight perpendicular, the weight parallel, here's the weight parallel, the answer for the weight parallel. So now we're just going to substitute 1151.124 minus this one, 167.5.899. And then now the answer, 1151.124 minus 1675.899. We're going to get a negative 524.775 Newton, which is the same as the one that we did previously. We see that the answer is negative. So it means now this object, it slides by itself. Slide by itself. That's why we get a negative answer here. For any other questions, you can contact us on our social media platforms, Facebook, WhatsApp, and Twitter. We are always available to help you. Thank you.